Hi everyone, this is Maths4Uni. This is the worked solution to question 8 from the worksheet corresponding to lecture 3. If you find this content helpful, then please consider liking and subscribing. The question says, the Leibniz rule is the generalization of the product rule for differentiation to n derivatives. It asks you to expand f of x times g of x double prime, and then the same for triple prime and quadruple prime, i.e. 2, 3, and 4 derivatives of this product by using the product rule repeatedly, and then it says to look at the coefficients for each one, and hence state and prove the Leibniz rule. So let's take this question one step at a time, and hopefully at the end we'll be able to state and prove the Leibniz rule. So firstly, if we expand f of x times g of x differentiated twice, where f of x and g of x are just some generic functions, if we expand out one of the differentiations, then we will have f prime of x, g of x, plus f of x, g prime of x, and then one more differentiation. This is just by expanding out the f of x times g of x with a single derivative, and then keeping our second derivative out here. And then if we apply the product rule again, then we will have f double prime of x times g of x from differentiating the f prime and leaving the g undifferentiated. And then we have f prime of x times g prime of x by leaving f prime as it is and differentiating g. And then over with this term here, we will have f prime of x times g prime of x by taking our f and differentiating and leaving our g prime alone. And then lastly, we have f of x times g double prime of x by leaving f alone and differentiating g prime. We notice that we can collect these terms here together, and so we will have f double prime of x times g of x, and then we have 2 of these f prime of x, g prime of x, and then we have our f of x times g double prime of x. This may look like a lot of terms, however, this kind of result can be helpful when differentiating several times for some kind of product. Next, we have the third derivative that we need to take. So we have f of x, g of x, differentiated 3 times. Well, luckily, we can just differentiate what we have above once more. So take what we have in the above, which is here, and differentiate it again. And if we do this, going slightly faster this time, then we will have f triple prime of x times g of x plus f double prime of x, g prime of x, plus 2f double prime of x, g prime of x, plus 2f double prime of x. That's not a double prime, it's just a single prime, with g double prime of x, and then we have f prime of x, g double prime of x, and f of x with g triple prime. As you can see, it is quite easy to make a mistake when differentiating this many functions. So if we try and collect together things that look the same, we notice that f double prime g prime appears here and here, so we're going to get 3 of those, and similarly f prime and g double prime. Again, we'll have 3 of those as well. And we would expect to get the same number because this result should be symmetric in f and g, because we have f times g differentiated, and there's no reason to prefer one of f or g over the other. And so if we collect these terms together, we will have f triple prime of x, g of x, plus 3f double prime of x, g prime of x, plus 3f single prime with g double prime, and then the last term, which is f of x with g triple prime of x. You may start to see the pattern of how these coefficients are building up. We have essentially 1, which is here, 2 and 1 for this second derivative, and we have here 1, 3, 3, 1 here. You might like to guess, if you're already aware of the pattern, what the next set of coefficients will be. But in the end, if you're not aware, we will prove the corresponding result anyway. So for the next one, I'll leave it as an exercise to go through the entire differentiation again, but all we're going to do is to take what we have above and differentiate once more. The result is, if we differentiate this 4 times, again, differentiating the above here once more, then we will get the very long expression f with 4 derivatives times by g plus 4 with f and 3 derivatives times g prime, and then 6 f with 2 and g with 2, 4 f with 1 and g with 3, and then finally f with none but g with 4. So hopefully now, at this point, now that we have the 1, 4, 6, 4, 1 set of coefficients for the 4th derivative, hopefully you're starting to see the pattern. These coefficients are in fact binomial coefficients. If we write out Pascal's triangle, which starts with 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, and then we can keep going, say 1, 5, 10, 10, 5, 1, and so on. Recalling that Pascal's triangle, we take the previous 2 elements, say we have this 3 here, we take the 1 and the 2 directly above to the left and the right, add them together, and we get this number 3 here. For example, this 10 here we get from the 6 and 4 here, and this is how Pascal's triangle is generated. We notice that we have these coefficients in the results that we've derived above. This row here, 1, 2, 1, corresponds to the second derivative, 1, 2, 1. This next row, 1, 3, 3, 1, corresponds to the third derivative, 1, 3, 3, 1. And then next we have 1, 4, 6, 4, 1, and that corresponds to the 4th derivative, 1, 4, 6, 4, 1. And so we can state the Leibniz rule based on our pattern that we've observed, but we will need to prove it afterwards. So let's write down our conjecture. We will have the following conjecture for the Leibniz rule. If we take f of x times g of x, and we differentiate n times in general, and we write this by writing an n in brackets up here to mean differentiate n times, we conjecture that this is the sum of quite a lot of terms in general. This is because up here, for example, we have, let's have a look, we have 5 terms in here, we have 4 in the previous and 3 in the one before that. So this will be a sum from k equals 0 up to n, where we're going to index each of our terms in the sum by k, and each term in the sum will look like f with n minus k derivatives times by g with k derivatives. For example, the first term will be f with n derivatives and g with no derivatives. The next term will be f with n minus 1 derivatives and g with 1 derivative, just like we have in the pattern we have here, f with 4 and g with none, and then f with 3 and g with 1, then f with 2, g with 2, and so on. But we're interested in what the coefficients are, and we have conjectured that we have binomial coefficients, i.e. we have the combination n choose k as our coefficients. So let's prove this result, and the best way to prove it in this case is to use induction. So we start with our base case, which we can take to be n equals 1. And so what do we have for n equals 1? What does our conjecture say? It says that f of x times g of x differentiated once is equal to the sum from k equals 0 up to 1 of 1 choose k, f of 1 minus kx, that's 1 minus k derivatives, and g with k derivatives. So we can write out the terms in this sum because there are not very many at all. In fact, we start with k equals 0. This gives us 1 choose 0, f with 1 minus 0 derivatives, and g with 0 derivatives, plus the other way around. So 1 choose 1 for k equals 1, with f of 1 minus 1 derivatives, and g with 1 derivative. It's worth being aware what we mean by 0 derivatives. If we take 0 derivatives of a certain function, then that just returns that original function. So this here is just g of x, this here, because 1 minus 1 is 0, is just f of x, and this here is f prime of x, the first derivative, and this here is g prime of x. These binomial coefficients are just 1 and 1, and so the result is f prime of x, g of x, plus f of x times g prime of x. And indeed, we recognise this as being the correct result from the product rule. F of x times g prime of x differentiated once is f prime g plus g prime f, or fg prime. And so, indeed, our base case is satisfied. So next we should have our inductive assumption. We assume that for a fixed value of n, that f of x times g of x differentiated n times is equal to the sum from k equals 0 up to n of n choose k with f to the n minus k derivatives and then g with k derivatives. And so next we should take our inductive step, i.e. we should look at differentiating our product f times g n plus 1 times. So how exactly should we relate this differentiation n plus 1 times to our inductive assumption which occurs for n derivatives? Well, we can do this by first taking f times g, differentiating this n times, and then differentiating the entire result once more. Then we can stick in our inductive assumption here for f times g differentiated n times into here with the summation, and this will give us the sum from k equals 0 up to n with n choose k, f n minus k x, g k x, and then this whole thing differentiated once more. Then we can appeal to linearity of differentiation, i.e. this differentiation here only really applies to the functions of x in here, not these coefficients here, and also it can distribute over the sum here. To see why this is, consider differentiating sine of x plus 2 cos of x. When you do this, you take sine of x, differentiate that and get cos of x, and you differentiate the cos of x and get minus sine of x, and then put it all together to get cos of x minus 2 sine of x. When you do that, you're really using linearity of differentiation. The derivative can be distributed over the sum of two terms and also ignores any constants like the 2 in the example that I just gave. So in this case, this will give us the sum from k equals 0 up to n with the binomial coefficient n choose k, and then we have our fn minus k x with gk x, and then all of this is differentiated once. So then we can use the normal product rule to perform this differentiation. This gives us, again, the sum k equals 0 up to n of n choose k, and then what do we have from the normal product rule? Well, we can first differentiate f once more, which gives us f with n minus k plus 1 for the number of derivatives, and then we have g with k. Similarly, you can do the same to g, and so we'll have f with n minus k, and we'll have g with k plus 1. At this point, it's worth stepping back and considering what we want to show. We want to take f of x times g of x, differentiate n plus 1 times, and get the sum from k equals 0 up to n plus 1, and then n plus 1 choose k with f n plus 1 minus k derivatives and g with k derivatives. So this is what we want to show. We were considering this left-hand side above, and we'd gotten to this sum here, and so we want to show that we can end up with a summation that looks a little bit like this. So let's consider each of the terms in this summation here separately, i.e. this sum with this term and this sum with this term. Firstly, we have the sum from k equals 0 up to n of n choose k, and then f with n minus k plus 1 derivatives, and g with k derivatives. And if we make a slight adjustment to this differentiation here by reordering the 1 and the k, this is the same as the sum from n equals 0 up to k, n choose k, and then we just write n plus 1 minus k in here. And the nice thing about that is that it makes our summand here look exactly the same as the summand up here. The word summand just refers to an expression inside a sum. Technically, the summand is the entire expression, including this coefficient here, but at least for now, we have these two things matching. Next, if we look at the other term, which is the sum from k equals 0 up to n, with n choose k, and then f with n minus k derivatives, and g with k plus 1. For this term, we want to get it looking, again, kind of like this thing here. And the way we can do that is by changing the index of our sum. We can subtract 1 from each of our k's inside the sum, and then add 1 to all of the k's that we index by out here. And so, if we do that, this gives us the sum. We have k equals 1 up to n plus 1, and then now we subtract 1 from all the k's inside, which gives us n choose k minus 1, and then we have f, and if we write this in a slightly different way with k minus 1 replacing k, then we have n plus 1 minus k matching the above up here, which is a good sign. We have our x dependence, and then we have our g with our k derivatives. Again, this matches the same function that we have above. And so, therefore, if we have our original left-hand side, which all the way up here was the n plus 1th derivative of f times g, which we'll write down again, fg n plus 1 derivatives. If you recall, this is equal to, let's have a look, this sum here, and we evaluated each of the individual terms in the sum here and here, which we did below. And if we put this all together, then we will have, it turns out, the sum, and bear with me for a moment here while I explain this, from k equals 0 up to n plus 1, and then these two things here added together. But again, we can factorize out these functions here, and so we have n choose k plus n choose k minus 1 with these functions, which also appear outside as factors, still inside the sum though. And again, this kind of needs slightly explaining, because each of our terms that we have here and here don't actually have the right indices on them which we have here. This one has, we've written the wrong thing here, that's brilliant. Okay, that's supposed to be k equals 0 up to n. Hopefully some of you eagle-eyed viewers would have spotted that. We have k equals 0 up to n here, and somehow here we've got k equals 0 up to n plus 1, and here we have k equals 1 up to n plus 1, i.e. k equals 0 is ignored. But I ask you as an exercise to check the edge cases, i.e. the n plus 1 in this first sum and the 0 in the second sum. Essentially, it's the same thing that we discussed in the video when dealing with binomial coefficients. The edge cases are not very nice for our binomial coefficients that we have in here, i.e. n choose k and n choose k minus 1. But either way, if we just proceed, assuming that you've checked the edge cases in your own time, then we can use the formula for adding up binomial coefficients of this form, and we have n choose k plus n choose k minus 1, and we discussed in the video that this is equal to, let's have a look, n plus 1 choose k. And so, finally, if we put this into here, then we have that this n plus 1 derivatives here is equal to the sum from k equals 0 up to n plus 1 of n plus 1 choose k, and then f with n plus 1 minus k, and g with k derivatives. And indeed, this is what we wanted to show. And so we are done by induction, and this gives us the Leibniz Rule. If you found this content useful, then please consider liking and subscribing. Thanks for watching, and goodbye for now.